Picture a teenage star, not a metaphor, a literal star, perhaps 60 million years old, barely an infant by cosmic standards, sitting at the heart of a nursery of gas and dust, still wrapped in the swaddling material from which it was born. The light it throws is harsh and blue and young. The disk of debris spinning around it hasn't yet decided what it wants to become. Somewhere in that disk, clumps of matter are gathering, pulling each other closer, squeezing themselves into spheres under their own gravity. Some of those clumps will become rocky planets like the Earth you're standing on right now. Some will become gas giants like Jupiter. And some, the ones that gather just a little too much mass, the ones that find themselves in exactly the wrong place at exactly the right time, will become something else entirely. Something that, until very recently, we didn't have a word for. Or rather, something that we thought we had a word for, and we were wrong. JWST, the James Webb Space Telescope, has just done something extraordinary. It hasn't just found a new object. It hasn't just captured a pretty picture of a distant nebula, or measured the chemical signature of some faraway atmosphere. It has looked directly into the hearts of objects sitting at the boundary between planets and stars, and it has told us, with an authority that no previous telescope could muster, that the boundary we drew in our textbooks was in the wrong place. Not slightly wrong, not off by a margin of error. Wrong in a way that forces us to rebuild one of the most fundamental categories in all of planetary science, and possibly in all of astronomy. What exactly did JWST find? Why does it change how we classify nearly everything in the outer solar system and beyond? And what does it mean for the way we define a planet, a star, and everything in between? Let me start with the telescope itself, because not everyone watching has been following JWST's story from the beginning, and the instrument matters enormously here. You cannot understand why this discovery is so significant without understanding what JWST can do that nothing before it could. The James Webb Space Telescope launched on Christmas Day 2021, a date that felt almost suspiciously poetic, given the magnitude of what it was about to deliver to science. It had been decades in the making. Literally decades. The original concept was sketched out in the mid-1990s, when the Hubble Space Telescope was still being celebrated for the first time after astronauts corrected its blurry vision. The people who proposed Webb were essentially saying, Hubble is magnificent, but it looks at the universe in visible light, the same light your eyes can see. What if we built a telescope that looked at the universe in infrared? Now, for those who haven't thought about the electromagnetic spectrum since school, visible light is just one narrow slice of all the radiation that exists. Think of it like the full keyboard of a piano versus a single octave in the middle. Most of what the universe is saying, it's saying in wavelengths your eyes can't detect. Infrared is the language of heat. Every warm object, a human body, a cup of tea, a newborn star still wrapped in gas, glows in infrared even when it's invisible to ordinary light. And crucially, infrared light passes through dust clouds that would completely block visible light. Dust that makes whole stellar nurseries opaque to Hubble renders them transparent to Webb. This is important because the objects at the centre of our story, the objects Webb just redefined, are born in dust. They form in the coldest, densest, most obscured corners of star-forming regions. They're the quiet ones, the dim ones, the ones that Hubble could only glimpse as faint ambiguous smudges. To Webb they glow like lanterns in a fog. Webb's primary mirror is also extraordinary. It's 5 meters across, more than 2.5 times the diameter of Hubble's mirror, made of 18 hexagonal segments of gold-plated beryllium, each one tuned to nanometer precision. The whole thing is so sensitive that, as the astronomers who built it like to say, it could detect the heat of a bumblebee at the distance of the moon. That is not a metaphor to make Webb sound impressive for a YouTube video. That is the actual sensitivity figure the engineering teams used when specifying the telescope's requirements. Webb sits at a location called Lagrange Point 2, a gravitational sweet spot, roughly 5 million kilometers from Earth in the direction away from the Sun, where the gravitational pulls of the Earth and Sun balance in a way that lets the telescope maintain a stable orbit while keeping its sun shield, a 5-layer structure the size of a tennis court, permanently pointed toward the sun. That shield keeps the telescope cold, and cold matters because infrared detectors are sensitive to heat, including their own. Webb operates at roughly 233 degrees Celsius, colder than most of outer space, so that the faint infrared glow of distant objects isn't drowned out by the instrument's own warmth. This is the machine JWST is. This is what's pointed at the sky right now, and over the past 3 years, it has been doing something that its builders designed it for. But that has yielded results more surprising, more disorienting, and more wonderful than almost anyone anticipated. It has been staring at brown dwarfs. Specifically, it has been staring at the very smallest, dimmest, coldest brown dwarfs it can find. The ones right at the line. The ones sitting exactly at the edge of the territory that we thought we'd mapped. The territory where planets become stars. But before we get to what Webb found in that territory, I want to spend a moment on something that rarely gets enough time in videos about JWST, and that is the sheer audacity of building this telescope at all, because it nearly didn't happen. The James Webb Space Telescope was originally scheduled to launch in 2007, then 2011, then 2018, then 2019, then 2021. The delays were not bureaucratic laziness or funding politics, though both of those things played a role at various points. They were the product of a machine so ambitious, so technically demanding, so far beyond anything ever attempted in space telescope engineering, that the people building it kept discovering new categories of problem that hadn't existed when the previous deadline was set. Think about what Webb actually is, physically, for a moment, not as a specification sheet, as an object that had to be assembled and tested and folded up and launched, and then unfolded in deep space. The primary mirror is too large to fit inside any rocket fairing in one piece, so it was designed to fold. 18 hexagonal mirror segments, hinged like the pages of a book, folded flat for launch and then unfolded, one by one in a precise choreographed sequence, once the telescope was in space. Each segment had to be individually actuated to a position accurate to within 1/20,000th the width of a human hair. Not approximately, exactly, because even a tiny misalignment would smear the focus, and a smeared focus on an instrument this sensitive would mean the whole thing was useless. The sunshield had to unfold too. 5 layers of material, each one thinner than a human fingernail, stretched across a structure the size of a tennis court. The layers had to be tensioned perfectly. Too loose and they'd flap in the faint solar wind and vibrate the mirror. Too tight and the stress could tear them. There were 3 of 44 individual single-point failure mechanisms in Webb's deployment sequence, meaning 344 places where if one specific thing went wrong in one specific way, the entire mission was over. No repair, no second chances. Hubble could be serviced by astronauts, because it orbits only a few hundred kilometers above Earth. Webb is 1.5 million kilometers away. Nothing can reach it. The engineers at Northrop Grumman and NASA's Goddard Space Flight Center tested every one of those 344 mechanisms, multiple times, in vacuum chambers, at cryogenic temperatures, in conditions designed to simulate the environment of deep space as faithfully as possible on the surface of a planet with gravity and air. They built and rebuilt. They found failures in testing and redesigned. They found contamination issues when particles from one component deposited on another. They found harmonic resonances, vibration frequencies, where the telescope structure would have amplified the vibrations of its own mechanisms, like a wine glass shattering at the right note. They fixed everyone when Webb finally launched on that Christmas morning in 2021 from the Guiana Space Center in Kourou, French Guiana, atop an Ariane 5 rocket. The entire 30-year project was staked on a deployment sequence that would take 29 days to complete, and that could not be interrupted, rewound, or corrected once it began. The mission operations team at the Space Telescope Science Institute in Baltimore monitored every step, every actuator confirmation, every temperature reading, every confirmation that the next fold had unfolded. It all worked, every single step. The 344 single-point failures were all avoided, the mirror segments aligned, the sunshield tensioned, the detectors cooled to their operating temperature. And on July 12, 2022, 6 months after launch, NASA released Webb's first full-colour science images to the world. I want to dwell on that for a moment, because it matters to the story we're telling. Those images of galaxy clusters, of stellar nurseries, of the spectra of exoplanet atmospheres, were not just pretty pictures. They were the first fruits of 30 years of human determination to see something that had never been seen before. Every image Webb sends back carries within it the memory of every engineer who redesigned a mechanism, every scientist who rewrote a proposal, every program manager who fought to keep the project funded during the years when its cost overruns threatened to cancel it entirely. Dr. John Mather, the Nobel Prize-winning astrophysicist, who served as Webb's senior project scientist from the very beginning, said something in an interview after the first images were released that I've thought about many times since. He said the telescope was not built to answer specific questions. It was built to find questions we hadn't thought to ask yet. The universe, he said, always surprises us. Webb was built to be surprised. The Jumbos, the objects that don't fit the line between planets and stars, are exactly the kind of surprise he meant. To understand what JWST found, you need to understand what that boundary looked like before. And to understand the boundary, you need to understand what, until now, was sitting on either side of it. On one side, planets, specifically the gas giants. Objects like Jupiter in our solar system, enormous spheres of hydrogen and helium that formed from the leftover material of a protoplanetary disk around a star. Jupiter is roughly 318 times the mass of Earth, which sounds enormous until you put it next to a star. The Sun is roughly 1,000 times the mass of Jupiter. Jupiter and objects like it, Saturn, Uranus, Neptune, and the many so-called hot Jupiters and super Jupiters discovered orbiting other stars are fundamentally objects of cold assembly. They formed from the outside in, sweeping up material that condensed in the cool outer regions of a disk. They never ignited. They are, at their cores, just very large piles of the same stuff that's everywhere in the universe. Hydrogen, helium, a scattering of heavier elements, compressed by gravity but never hot enough or dense enough to light the fusion fire. On the other side of the line, stars. Even the smallest stars, the red dwarfs, the M dwarfs, the dim smouldering coals at the bottom of the stellar luminosity function, are doing something fundamentally different from Jupiter. They are fusing hydrogen in their cores. Hydrogen fusion is not just a chemical process burning fuel. It is the conversion of matter into energy via Einstein's E mc², the release of the energy locked inside the nuclei of atoms. A star is not a fire. It is a slow, sustained nuclear explosion, self-regulated by the pressure of the radiation it produces pushing outward against the gravity pulling inward. That balance, the gravitational squeeze versus the radiation push, is the secret of stellar longevity. Our Sun has been burning for 4.6 billion years. It will burn for roughly another 5 billion. The smallest red dwarfs will burn for trillions of years. Between these two categories, for decades, there was a middle ground, and in 1995 astronomers gave that middle ground a name, brown dwarfs. The name was coined by Jill Tarter, the same astrophysicist whose work partly inspired the film Contact, and it was meant to capture the sense of something in between. Not red like a star, not the reflective blue-white of a gas giant, brown, ambiguous, neither one thing nor the other. Brown dwarfs are objects too massive to be ordinary planets. They generally have more than about 13 times the mass of Jupiter, but not massive enough to sustain the kind of hydrogen fusion that defines a star. The lower limit for stable hydrogen burning is roughly 80 Jupiter masses. Objects between 13 and 80 Jupiter masses occupy this brown dwarf zone, burning deuterium, a heavier form of hydrogen, for a while before cooling and fading as their fuel runs out. They're the failed stars, the almost suns, the not-quite planets. That was the picture we had. It was clean. It was logical. It was taught in undergraduate astronomy courses as one of the foundational taxonomies of astrophysics. And it was wrong, or more precisely, it was incomplete. and the incompleteness was sitting right at the boundary. Here is where JWST enters the story directly. In early programs from Webb's first 2 years of science operations, astronomers began surveying the Orion Nebula cluster, one of the richest stellar nurseries in our galaxy, roughly 1,344 light-years from Earth, close enough for JWST to resolve individual objects with extraordinary detail. The Orion Nebula cluster is a chaotic, glorious laboratory. It contains hundreds of young stars, and scattered around those stars, in regions previously too dark and dusty for any other telescope to properly study, it contains something else, hundreds of what are now being called jumbios. Jupiter Mass Binary Objects. The name comes from the Discovery team's paper led by Dr. Mark McCaughrean, Senior Advisor for Science and Exploration at the European Space Agency, alongside Dr. Samuel Pearson. When McCaughrean and Pearson published their results in October 2023, based on JWST imaging of the Orion Nebula, they announced the detection of at least 540 rogue planetary mass objects in the cluster, objects with masses between roughly 1 and 13 times the mass of Jupiter, drifting free of any host star. These weren't planets orbiting a star that Webb had somehow caught in transit. These were free-floating objects, wandering alone through the nebula, gravitationally unattached to anything. Many of them, 42 pairs in that first detection, were orbiting each other. Pairs of objects, each roughly the mass of Jupiter, circling a common centre of gravity, together, alone in the dark. Let that sit for a moment. 2 Jupiter mass objects orbiting each other, drifting through a stellar nursery with no parent star, no disk, no system, just each other. This was already deeply strange, but that's not the part that redefined the boundary. The part that redefined the boundary came from what JWST found when it looked more carefully at where these objects sit on what astronomers call the mass function, the statistical distribution of how many objects exist at each mass level, from the least massive to the most. Here is the discovery stated plainly. There is no clean break. There is no sharp line in the data where objects on one side behave like planets, and objects on the other side behave like brown dwarfs. When JWST resolved objects in the Orion Nebula down to masses as low as 1 Jupiter mass, a regime where no telescope had previously had the sensitivity to count individual objects reliably, the distribution of objects was continuous. Smooth, it didn't jump or gap or skip. It slid downward continuously from the mass range of known brown dwarfs into the mass range of giant planets. Which means the boundary we'd drawn was not a boundary in nature. It was a boundary in our own ignorance, Doctor. McCaughrean put it plainly in public statements following the paper's release. The discovery, he said, challenges the standard models of both star formation and planet formation because these objects should not exist under either model. They're too small to have formed the way stars form, by the gravitational collapse of a gas cloud. They're too isolated to have formed the way planets form, by accreting material in a disk around a host star. They're something else. Or they're both things at once. Or our categories are simply the wrong shape for the reality we're looking at. The data from JWST went further still. Using its near-infrared camera, NIRCam, and its near-infrared spectrograph, NIRSpec, Webb began taking spectra of these planetary mass objects. A spectrum is essentially a fingerprint. When light passes through matter, different atoms and molecules absorb different colours, leaving gaps in the rainbow of the light that reaches your detector. Those gaps tell you what chemicals are present. For stars, the spectrum tells you temperature, chemical composition, age. For planets with atmospheres, it tells you what the atmosphere is made of. For the jumbios, for these free-floating objects in Orion and in other star-forming regions subsequently observed by Webb, the spectra told a story that didn't fit neatly into either the stellar category or the planetary category. The objects showed molecular water, they showed methane, they showed carbon dioxide. These are the signatures of cool, chemically complex atmospheres. Atmospheres more like those of the giant planets in our solar system than like those of stars. But the objects that showed these signatures included some that were massive enough that under the old classification scheme, they should have been called brown dwarfs. The chemical dividing line didn't match the mass dividing line, And this is where the redefinition happens in its most fundamental form. Kevin Luhman of Penn State University, one of the world's leading experts on brown dwarfs and low-mass objects, had been arguing for years, in papers that were technically thorough but that lacked the observational firepower to fully convince the community, that the boundary between planets and brown dwarfs needed to be rethought. His argument was not just about mass, it was about formation mechanism. Luhman proposed that what distinguishes a planet from a brown dwarf should not be a number on a scale, not 13 Jupiter masses as the magic threshold, but rather the process by which the object formed. A planet, in Luhman's framework, forms with a circumstellar disk by core accretion or disk instability. A brown dwarf forms by the collapse of a gas cloud, the same process that forms stars. The mass at which objects form from disk material versus from cloud collapse can overlap, which means you can have a 5 Jupiter mass object that is, by Luhman's definition, a brown dwarf, and a 15 Jupiter mass object that is a planet. Before JWST, this was a theoretical argument. You could debate it in the literature. You could run simulations. But you couldn't look directly at the population of objects near the boundary and count them and measure their spectra and determine empirically what the distribution looked like. Now you can. And the data says the mass threshold of 13 Jupiter masses is not a line in nature. The 13 Jupiter threshold was chosen because it's roughly the point at which deuterium fusion becomes possible. Deuterium being a heavier isotope of hydrogen that fuses at lower temperatures and pressures than ordinary hydrogen. Objects above 13 Jupiter masses can burn deuterium for a brief period. Objects below cannot. This seemed like a physically meaningful threshold. But JWST spectra show that deuterium burning, or the lack of it, does not produce a detectable change in the chemical signatures of these objects' atmospheres. The chemistry above and below 13 Jupiter masses is not dramatically different in the way you'd expect if that mass threshold represented a real physical transition. The objects look like a continuum. They form a spectrum, not just in the astronomical sense, but in the English language sense. A gradation. A slide from one thing into another. The IAU, the International Astronomical Union, the body that famously reclassified Pluto as a dwarf planet in 2006, does not yet have an official position on the implications of JWST's findings for the definition of a planet. But multiple review papers, including one published in 2024 by a consortium of researchers across ESA, NASA and several European universities, have called explicitly for a revision of the working definition. The line, they argue, needs to move, or perhaps the line needs to stop being a line at all. I want to make sure the scale of what we're talking about is clear here, because the phrase mass function is doing a lot of work in that sentence, and I don't want to rush past it. A mass function, in this context, is one of the most fundamental tools astronomers have for understanding how nature builds things. It's simple in concept. You count objects of different masses in a given region of space, plot the number of objects on one axis and the mass of those objects on the other axis, and see what shape the graph makes. For stars, this has been studied for decades. The result is called the initial mass function, the IMF, and it has a very well understood shape. There are many more low-mass stars than high-mass stars. If you go from massive blue giants to medium-sized stars like the Sun to Solstice red dwarfs, the number of objects at each mass level rises steeply as you go to lower and lower masses. The universe makes far more small stars than big ones. This was first quantified by Edwin Salpeter in 1955, and the Salpeter initial mass function has been one of the bedrock results of stellar astrophysics ever since. The question that had never been satisfactorily answered before JWST was, what happens when you extend that function downward, past the bottom of the stellar sequence, through the brown dwarf regime and into the regime of planetary mass objects? Does the function keep rising, meaning the universe makes even more free-floating planetary mass objects than it makes brown dwarfs? Does it flatten off, meaning the rate of object production per unit mass stays roughly constant? Or does it turn over and fall, meaning below some threshold, the universe stops making free-floating objects efficiently, and you really are in a different physical regime? Pre-JWST surveys, Using Hubble, Spitzer, ground-based adaptive optics systems like those on the Very Large Telescope in Chile, suggests the function turned over somewhere around 5 to 10 Jupiter masses. Below that, the surveys found almost nothing. The graph appeared to fall off a cliff. This was taken as evidence that 5 to 10 Jupiter masses was a natural lower limit for the mass of an object that could form by cloud collapse. Below that mass, the thinking went you simply couldn't form an object in isolation. You needed a disk. What JWST showed is that the cliff wasn't real. The graph didn't fall, it continued. And the previous surveys hadn't seen the continuation, not because the objects weren't there, but because the objects below 5 Jupiter masses are so dim, so cold, so faint in the infrared, that Hubble and Spitzer and even ground-based adaptive optics systems simply didn't have the sensitivity to detect them individually in the crowded, dusty environment of a stellar nursery. Webb does. And when Webb looked, it found the bottom of the cliff was just the point at which the previous telescopes had gone blind. Below it, the population continues. This is in a technical sense a detection bias problem. Scientists have a name for it, Malmquist bias, after Swedish astronomer Gunnar Malmquist, who described the phenomenon in the 1920s. Think of it like this. Imagine you're trying to count all the cars on a highway at night from a great distance. You can only see cars whose headlights are bright enough to reach you. Small cars with dim lights are invisible. You'd count mostly large vehicles with bright lights and conclude that the highway is dominated by trucks. But the trucks were never the majority. They were just the most visible. The small cars were always there. You just couldn't see them. Pre-JWST surveys of planetary mass objects in stellar nurseries were counting trucks. Webb can see the small cars, and there are a lot of small cars now. Let me tell you something that makes this result even more striking. The Orion Nebula cluster is not an old region. It's roughly 1 to 3 million years old, a cosmic eye blink. The objects Webb found in it have had almost no time to migrate, scatter, or be ejected from wherever they formed, which means the population of free-floating planetary mass objects Webb is counting reflects, more or less directly, the output of the formation process. These aren't objects that formed somewhere else and drifted in. They formed here, in this cluster, under these conditions, and there are hundreds of them. That last point bears repeating, because it's the one that sits in your chest when you really let it land. The Orion Nebula cluster is a young region of our galaxy, close enough for Webb to study in detail, and in just this one region, Webb found over 500 free-floating objects in the planetary mass range. If Orion is even remotely typical, and there's no reason to think it's unusual, then the galaxy contains an almost incomprehensible number of these things. Not billions, not trillions, far more than the number of stars drifting through interstellar space, silent, cold, carrying no light of their own, reflecting no star's glow, visible only to an instrument patient enough and cold enough and precise enough to detect the faint warmth of their own slow cooling. They have been there the whole time. We just built the eye to see them. Let's slow down and talk about the actual physics here, because this is where the story gets genuinely strange and genuinely beautiful. Think of the difference between baking a loaf of bread and finding a rock on a riverbed. The bread is assembled, you put ingredients together in a process, and the structure of the bread reflects that process. The rock is carved, it starts as part of a larger mass and is shaped by erosion into what it becomes. These are two fundamentally different ways of making an object. And they produce objects with different internal structures, even if they end up similar sizes. Stars and brown dwarfs form by something closer to the second method. A cloud of gas and dust, typically cold molecular hydrogen, laced with trace amounts of helium and heavier elements, begins to collapse under its own gravity. Perhaps a shockwave from a nearby supernova gives it a push. Perhaps it simply grows dense enough in one spot that the gravitational pull of that concentration draws in more material. The collapse accelerates, the centre heats, the pressure builds. If enough mass falls inward, the core becomes hot enough and dense enough to ignite hydrogen fusion. A star is born. If not quite enough mass accumulates, The core gets hot enough to burn deuterium briefly, but not hot enough for sustained hydrogen fusion. A brown dwarf emerges, glows for a while, and then cools forever. The object formed in one piece from the top down. Planets, at least in the textbook model, form by the first method. A disk of material surrounds a young star. In that disk, tiny grains of dust and ice collide and stick together. Millimeter-sized grains become centimeter-sized pebbles. Pebbles become kilometer-sized planetesimals. Think of the asteroid belt, which is full of planetesimals that never got their act together. Planetesimals grow into planetary embryos. Embryos merge into full planets. This process, core accretion, is how we believe the rocky inner planets of the solar system formed. For gas giants like Jupiter, the process is slightly different. A large rocky or icy core forms first, and then its gravity is strong enough to rapidly accrete a vast envelope of gas from the disk. The object is assembled from the bottom up. These are the two pathways. Top-down collapse makes stars and brown dwarfs. Bottom-up assembly makes planets. The 13 Jupiter mass threshold was supposed to mark the approximate boundary between these two pathways, because it's the threshold below which an object can't burn deuterium. The first tentative sign that it formed with enough mass to at least partially ignite. Objects above the threshold, the thinking went, formed top-down. Objects below formed bottom-up. JWST broke this logic in two ways simultaneously. First, by finding the Jumbos, the free-floating planetary mass objects in Orion. These objects have masses well below 13 Jupiter masses, some as low as 1 Jupiter mass, and yet they are not in disks. They are not orbiting stars. They did not form bottom-up in a protoplanetary disk. They are drifting free, which means either they formed top-down by cloud collapse at a mass far lower than we thought was possible, or they formed in disks and were subsequently ejected from their systems by gravitational interactions. A process that computer simulations show is genuinely possible, but that had never been observed at this scale and this frequency. Corgrian and Pearson's analysis of the Jumbio population suggests that ejection alone cannot account for all of them. If you run the numbers, count how many systems in the Orion Nebula cluster you'd expect to have, and estimate how many planets you'd need to eject per system to produce the observed number of free-floating objects. The numbers don't balance. You'd need far more ejections than current models predict, which means some of these objects probably formed in place, in the open nebula, by direct collapse. At Jupiter's mass, this was one of the most startling results JWST has produced in its first years of science operations. Second, JWST's spectroscopy of objects straddling the old 13 Jupiter boundary showed that the transition between planetary chemistry and brown dwarf chemistry in these objects' atmospheres does not happen at 13 Jupiter masses. It happens, if it can be said to happen sharply at all, at lower masses, and the transition is gradual rather than abrupt. Dr. Etienne Artigot at the Université de Montréal has led several of JWST's spectroscopic surveys of cold substellar objects, published analysis showing that the temperature at which an object's atmosphere starts showing the chemical hallmarks of a giant planet atmosphere. Methane absorption being the key diagnostic doesn't correspond to any fixed mass. It corresponds to a temperature, typically around 1300 Kelvin. And objects of different masses cool at different rates depending on their age and their composition, so the same 1300 Kelvin atmosphere might be found in an object of 8 Jupiter masses that is a few hundred million years old, or in an object of 20 Jupiter masses that is several billion years old. Temperature, not mass, turns out to be a better predictor of atmospheric chemistry than mass alone. Which means mass, the thing we've been using to draw the line, is in some fundamental sense the wrong ruler. Artigau's team didn't just suggest this theoretically, they showed it in data. Webb's near-spec instrument, working in its multi-object spectroscopy mode, which can measure the spectra of hundreds of objects simultaneously in a single observation, returned spectra of 19 objects in the young cluster IC 348, with masses ranging from below 5 Jupiter masses to above 15. The spectral features in these objects formed a smooth gradient. No cliff, no step, no sign that the universe recognized the 13 Jupiter threshold as anything meaningful. Let me give you one more figure to anchor this, because Astrom viewers appreciate precision. Dr. Catarina Alves de Oliveira, a researcher at the European Space Agency who works on JWST's early release observation program, has been tracking what her team calls the planetary mass object function, the number of objects at each mass level in a given star-forming region. When you plot this function using pre-JWST data from telescopes like Hubble, Spitzer, and ground-based infrared surveys, it looks like it falls off a cliff below about 5 Jupiter masses. Below that point you see almost nothing, not because there's nothing there, but because previous telescopes weren't sensitive enough to detect them. When you replot the same regions using JWST, the function doesn't fall off a cliff. It continues, smoothly, down to the detection limit of the telescope. And that detection limit is now around 1 Jupiter mass in nearby star-forming regions. The objects below 5 Jupiter masses were always there. We just couldn't see them, and now that we can, they look like a seamless continuation of the population above them. There's one more dimension of the spectroscopic story I want to walk through carefully, because it goes to the heart of why this discovery is not just a count problem, not just a matter of finding more objects than expected, but a chemistry problem. A problem about what these objects are made of and what that tells us about how they formed. Let me introduce you to something called the TC dwarf boundary. In the taxonomy of brown dwarfs, and yes, even within the category of brown dwarf, there is a subtaxonomy, because astronomers cannot resist classifying things. Objects are assigned spectral types based on their temperature. The hottest brown dwarfs, which glow dull red, are called L dwarfs. As you go cooler, you'll get T dwarfs, which show strong methane absorption in their spectra. That's the chemical signature of a cold hydrogen-dominated atmosphere, the same chemistry you find in Jupiter. And then, at the very bottom of the temperature scale, below about 500 Kelvin, you get Y dwarfs, objects so cold that their atmospheres are thought to contain water clouds, and possibly even salt and sulfide clouds, in the same way that Earth's atmosphere contains water clouds. Y dwarfs are the coldest brown dwarfs known. Some of them have surface temperatures barely above the boiling point of water. Before JWST, only a handful of Y dwarfs were known, and they were so faint that characterizing their spectra was extraordinarily difficult. You could detect them as faint dots of warmth in wide-field infrared surveys, particularly the WISE satellite survey, which catalogued the whole sky in mid-infrared wavelengths. But taking a spectrum of a Y dwarf, which requires collecting enough photons from the object to spread across hundreds of wavelength channels simultaneously, was at the very edge of what Hubble's infrared capabilities could do. The spectra were noisy, the chemical identifications were uncertain. The Y dwarf sequence, the coldest end of the brown dwarf temperature scale, was, before Webb, almost a theoretical construct. We knew these objects existed. We couldn't properly study them. Webb changed this overnight. Dr. Leila Hamoula, a postdoctoral researcher at the Institut d'Astrophysique de Paris, working within a larger JWST cold brown dwarf survey program, was part of the team that took Webb's first high-resolution spectra of Y dwarfs in 2023. The results, she described in a conference presentation, were like going from reading a blurred photocopy to reading the original typed page. The chemical features that had been smears and hints in Hubble data became sharp, unambiguous lines. Water absorption, methane absorption, ammonia, for the first time detected clearly in a substellar atmosphere outside the solar system. And in the coldest objects, those right at the bottom of the Y dwarf sequence, the faint signature of what appears to be molecular hydrogen collision-induced absorption, a feature so subtle that it had been predicted theoretically for decades but never cleanly observed. Why does this matter for our story? Because the Y dwarfs, the coldest brown dwarfs, overlap in temperature with the warmest free-floating planetary mass objects. When you take a spectrum of a Y dwarf and compare it to a spectrum of a free-floating object of, say, 6 Jupiter masses in a young cluster, the spectra look remarkably similar. Not identical, there are age-dependent differences, Because a young object of 6 Jupiter masses has had less time to cool than an old object of 15 Jupiter masses at the same temperature. But the chemical similarities are striking. The same molecules are present, the same absorption features appear in the same wavelength ranges. The spectroscopic gradient from warm brown dwarfs through cool brown dwarfs through white dwarfs and into free-floating planetary mass objects is again continuous. Dr. Hamula's group published a comparison spectrum in late 2023, a figure that has been reproduced in several review articles since, showing the spectral sequence from an L dwarf through a T dwarf through a Y dwarf and down to the coldest free-floating Jumbeo detected in Orion. Looks like a musical scale descending smoothly from one note to the next. No gaps, no jumps, no signature of a transition between physical regimes. This is the empirical foundation for the claim that the boundary has been redefined. It's not just a philosophical argument about categories. It's not just a statistical argument about mass distributions. It's a direct chemical comparison in high-resolution spectra, showing that the objects we call brown dwarfs and the objects we call free-floating planets share the same atmospheric chemistry, the same molecular inventory, the same spectroscopic fingerprint, differing only in temperature, which itself varies continuously with mass and age and formation history in a way that cannot be captured by any single threshold number. The 13 Jupiter mass boundary was a number chosen to demarcate a physical process, deuterium burning. JWST's spectroscopy is now showing that deuterium burning, even where it occurs, doesn't leave a lasting chemical stamp on an object's atmosphere. The atmosphere evolves chemically as the object cools, regardless of whether it briefly burned deuterium in its youth. Two objects, one that burned deuterium and one that didn't, can end up with atmospheres so chemically similar that you cannot tell them apart from their spectra alone, which means the process that the boundary was designed to mark is, observationally, undetectable in the object's current states. The boundary marks something that happened billions of years ago and left no trace you can read today. That's not a boundary, that's a historical footnote. And JWST has made this visible for the first time. Let me be honest with you about something. The astronomy community does not agree on what to do with this discovery. There are, broadly speaking, 3 camps, and each one is staffed by brilliant people looking at the same data and reaching different conclusions. Camp 1. Revise the mass threshold. The first group argues that the 13 Jupiter mass threshold should be abandoned as the definition of the lower boundary of brown dwarfs and replaced with a lower limit, perhaps 5 or even 3 Jupiter masses. Under this view, the category of brown dwarf expands downward to absorb the Jumbeos and the free-floating planetary mass objects that Webb has found. The argument is essentially taxonomic. We need a category for objects that form by collapse but are below 13 Jupiter masses, and calling them planets when they don't orbit anything is clearly wrong. A planet without a star is a misnomer, so call them brown dwarfs, lower the threshold and move on. Dr. Luhmann's own published view falls partially in this camp, though he prefers the formation mechanism approach over a simple mass revision. His 2024 review paper, published in the Astronomical Journal, makes the case that Planemo, a portmanteau of planetary mass object, should become an official category in its own right, distinct from both planets and brown dwarfs, defined by its mass range and its free-floating nature. Planemos would be objects between roughly 1 and 13 Jupiter masses that do not orbit a host star and whose formation history may include either ejection from a disk system or direct collapse. Camp 2. Formation mechanism above all the second group, which includes researchers like Dr. Jonathan Fortney at the University of California, Santa Cruz. One of the world's leading authorities on the interiors and atmospheres of giant planets and brown dwarfs, argues that the only scientifically coherent way to classify these objects is by how they formed. Full stop. Forget about mass thresholds. Forget about deuterium burning. An object that formed in a disk around a star, regardless of its mass, is a planet. An object that formed by cloud collapse, regardless of its mass, is a brown dwarf or a failed star. The problem, of course, is that we currently have no reliable observational method to determine for any given object whether it formed in a disk or by collapse. We can sometimes infer it from the object's current environment. A free floating object probably didn't form in a disk, but for objects orbiting host stars at wide separations, the ambiguity is essentially unresolvable with current technology. Fortney acknowledges this limitation. His position is that the right answer may be temporarily inconvenient. We can't always apply the formation mechanism criterion because we can't always determine the formation history. But that doesn't mean we should settle for a proxy criterion like mass that we know is physically wrong. It's a principled stance. It's also, practically speaking, a standard we can't fully meet yet, Camp 3. We need new categories entirely. The third group, smaller, but perhaps the most intellectually interesting, argues that the problem isn't where to draw the line. The problem is that we're trying to draw a line at all. Dr. Niku Madhusudan at the University of Cambridge, who leads a group focused on exoplanet atmospheres and who has published extensively on the chemistry of substellar objects, made this argument in a 2023 perspective piece in Nature Astronomy. The universe, Madhusudan argued, does not care about our classification systems. The objects we observe form a continuum in mass, in chemical composition, in temperature, in internal structure. The fact that our taxonomy requires a line between planet and brown dwarf says more about how human minds work, our preference for discrete categories, than it does about how the universe works. Physics is continuous. Our categories are not. Madhusudan's practical proposal is that astronomers adopt what he calls a property-based description, rather than a category-based one. Rather than labelling an object as a planet or a brown dwarf, publish its measured properties, mass, temperature, spectrum, orbital status, and let those properties speak for themselves. The category label becomes shorthand for a cluster of typical properties, rather than a bright dividing line. This is perhaps the most radical position among the three. It's also, if you take seriously what JWST is showing us, perhaps the most honest. The debate remains live. No consensus has emerged. The IAU Working Group on Extrasolar Planets is actively considering revisions to the working definition. Corgrian has spoken publicly about the need for the community to engage seriously with JWST's results, rather than retreating to pre-Webb definitions that were designed around pre-Webb data. Luhmann continues to publish, and his body of work on low-mass objects is now among the most cited in the field. Fortney's group continues to run atmospheric models. Madhusudan's team continues to extract every last photon of chemical information from Webb spectra, and the objects themselves, the jumbos, the free floaters, the planemos, whatever we end up calling them, continue to drift through the Orion Nebula, indifferent to the argument. I want to pause the forward momentum of the story for a moment, because there's a deeper pattern here that I think deserves its own chapter. The story of the planet-brown dwarf boundary is not a unique story. It is the latest installment in a very long sequence, decades long, arguably centuries long, of astronomers drawing lines in the sky and the universe quietly ignoring them. Let me take you through a few of those lines. Not to embarrass the scientists who drew them. They were doing the best they could with the instruments and data available to them, but because understanding the history of these failed classifications makes the JWST result feel less like a surprise and more like an inevitability. The first line that matters to our story was drawn in 1938 by a physicist named Hans Bethe, who would later win the Nobel Prize in Physics for this very work, worked out the chain of nuclear reactions responsible for energy production in the Sun. His paper, published in Physical Review in 1939, established the proton-proton chain and the carbon-nitrogen-oxygen cycle as the mechanisms by which stars convert hydrogen into helium. This was a genuine triumph of theoretical physics. For the first time, humanity understood, at a mechanistic level, what a star actually is. A furnace, a sustained nuclear reaction, a self-regulating engine that burns hydrogen. Implicit in Bethe's work was a line: below a certain mass, a collapsing gas cloud cannot ignite hydrogen fusion. The core doesn't get hot enough. The pressure doesn't get high enough. The proton-proton chain never starts. Below this mass limit, which we now place at roughly 80 Jupiter masses, or about 0.08 solar masses, you don't have a star. You have something else. What that something else was, nobody had a name for yet. And for the next 50 years, nobody knew for certain that it existed at all. The theoretical case for substellar objects too massive to be planets but too lightweight to be stars, was developed primarily through the 1960s and 1970s. Dr. Shiv Kumar, an astrophysicist at the University of Virginia, published the first detailed theoretical models of what he called black dwarfs in 1963. Objects below the hydrogen burning limit that would form, glow briefly on the heat of their own gravitational contraction, and then cool and fade. Kumar's black dwarfs were exactly what we now call brown dwarfs, right down to the mass range and the cooling behaviour. He had the physics correct. But no telescope of the era could detect such an object. They were too dim, so Kumar's prediction sat in the literature for 30 years, largely unverified. In 1995, the same year Jill Tarter coined the name brown dwarf. The first confirmed brown dwarf was announced. It was called Gliese 229b, a companion to a red dwarf star about 19 light-years from Earth, detected by a team led by Dr. Tadashi Nakajima at the California Institute of Technology using the Palomar Observatory's 60-inch telescope. Gliese 229b was cold enough, around 950 Kelvin at its surface, to show clear methane absorption in its spectrum, a chemical signature that could not be produced by any star. The detection was a triumph. Kumar's 32-year-old prediction was confirmed. Brown dwarfs were real, and the community exhaled. The line was validated. The category was established, or so it seemed, because what happened next, over the following decade, is a pattern that should now feel familiar. As detectors improved, as sky surveys became more sensitive, as infrared astronomy matured from a specialty into a mainstream tool, more and more brown dwarfs were found. Hundreds. The 2 MSS Sky Survey, the 2 Micron All-Sky Survey, completed in 2003, catalogued hundreds of L&T dwarfs across the sky. The WISE satellite, launched in 2009, found hundreds more, including the first white dwarfs. And as the population grew, the distribution of masses in that population started to look uncomfortable. The mass distribution of brown dwarfs, the plot of how many objects exist at each mass level, was expected by most models to fall off steeply as you approached the lower mass limit. There should be relatively few brown dwarfs near 15 Jupiter masses, the models said, and almost none below 13. The deuterium burning threshold was supposed to represent a natural floor below which the formation process became inefficient. The observed mass distribution didn't cooperate. It kept showing objects near and slightly below the expected floor, not enough to definitively shatter the threshold. The uncertainties in mass estimates for individual objects are large enough that a 12 Jupiter mass object might genuinely be a 14 Jupiter mass object measured with systematic errors, but enough to make several researchers uncomfortable. Dr. Adam Bergesser, now at UC San Diego, was among those who published analyses in the late 2000s and early 2010s noting that the mass function of brown dwarfs did not show the sharp turnover that the models predicted. "There's no cliff in the data," Bergesser said in a 2012 conference talk. "There's a slope, and slopes don't tell you where categories end." The community heard him. They noted the concern, and then they waited for better data, because the uncertainties in the mass estimates were large enough to leave the question genuinely open. JWST is the better data. There's a second line in this story, drawn not in mass but in orbital mechanics, and it matters because it reveals a structural problem with how we've been thinking about classification. In 2006, the International Astronomical Union met in Prague and voted to formally define the word planet for the first time in history. The vote was prompted by the discovery of Eris, an object in the outer solar system slightly larger than Pluto, and the broader recognition that the Kuiper belt was full of Pluto-sized objects that would all need to be called planets if Pluto was going to keep its status. The IAU's solution was to create three categories: planets, dwarf planets, and small solar system bodies. A planet, under the new definition, is an object that A. orbits the Sun, B. has sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium, nearly round shape, and C. has cleared the neighbourhood around its orbit. Pluto failed condition C. It shares its orbital neighbourhood with hundreds of Kuiper Belt objects. Pluto was reclassified as a dwarf planet. The vote was 8% of the IAU's total membership, cast in a room in Prague, and it removed a world from the list that it had occupied for 76 years. The internet did not take this quietly, but here's the part of the 2006 decision that matters for our story. Condition A orbits the Sun. The definition of a planet, as formally adopted by the IAU, requires that the object orbit our specific star. An exoplanet, a planet orbiting another star, is not technically a planet under the 2006 IAU definition. Neither is a free-floating planetary mass object. Neither is a planetary mass companion to a brown dwarf. This was not an oversight. The IAU Working Group on Extrasolar Planets published a working definition of exoplanets separately in 2003, which used the deuterium burning threshold of 13 Jupiter masses as the upper boundary of what counted as a planet. Below 13 Jupiter masses, planet. Above 13 Jupiter masses, brown dwarf. But this working definition was never formally adopted by the IAU General Assembly. It was explicitly described as a working definition, pending more data. That more data is now here, and what it shows is that both the 2003 working definition and the 2006 Prague definition have the same structural problem. They draw lines around categories based on specific, historically contingent observations, not on fundamental physical principles. The 2006 definition works reasonably well for our solar system because we know the orbital histories and formation circumstances of the 8 planets. But it fails completely for exoplanets, for free floaters, for objects in binary systems at wide separations where the clearing the neighbourhood criterion is physically meaningless. Dr. Jean-Luc Margot at UCLA, who has spent years analysing the IAU definition and its applicability to extrasolar systems, published a quantitative reformulation of the planet definition in 2015 that tried to make it applicable beyond the solar system. His definition uses a dimensionless parameter comparing the mass of the candidate object to the mass needed to dynamically clear its orbital zone around its host star that can be calculated for any object in any system. Under Margot's definition, Jupiter clears its zone by a factor of roughly 4,000. Earth clears its zone by a factor of roughly 800. Pluto fails to clear its zone by a factor of roughly 0.003. The definition is quantitative, applicable to exoplanets, and produces the same result as the qualitative IAU definition for solar system objects. But Margot's definition doesn't help with free-floating objects. An object that orbits no star has no orbital zone to clear. Under every definition currently available, 2003 working definition, 2006 IAU definition, Margot's 2015 reformulation, a free-floating planetary mass object is definitionally homeless. It doesn't fit into any existing category, and JWST has now confirmed that there are hundreds of them in just one nearby stellar nursery. This is the structural problem the community is now grappling with. It's not just that the 13 Jupiter mass threshold was in the wrong place. It's that the categories themselves, planet, brown dwarf, star, were designed around a set of examples that turned out to be unrepresentative. We designed our taxonomy around the solar system and a handful of brown dwarfs. We assumed the solar system was typical. We assumed that free-floating planetary mass objects were rare curiosities. We assumed that the categories we'd built for familiar objects would scale up cleanly to cover every object the universe could produce. None of those assumptions were correct. Dr. Jiba Basri at UC Berkeley, one of the pioneers of brown dwarf research, who was among the first to publish spectroscopic confirmation of brown dwarfs in the 1990s, wrote an essay in 2006, coincidentally the same year as the Prague vote, reflecting on the classification problem. "We keep trying to draw lines," he wrote, "in a space that the universe has filled continuously. The lesson of every generation of telescope is the same. The lesson is that the map isn't not the territory. The territory is always richer than the map." He was writing about brown dwarfs and the difficulty of defining them precisely. He could have been writing about JWST's findings 2 decades later. The sentiment is the same. The lesson is the same. We draw lines. The universe ignores them. And then, eventually, we build a better telescope. And the better telescope shows us what the universe was doing while we were busy arguing about the lines. That telescope right now is Webb. And what it's showing us is that the territory between the last star and the first planet is not a line, it's a landscape. A continuous, populated, chemically complex landscape stretching across 4 decades of mass. From the least massive free-floating orbs detected at barely 1 Jupiter mass, up through the brown dwarfs, up through the substellar objects that teeter at the edge of hydrogen fusion, and into the red dwarf stars at the bottom of the stellar sequence. The landscape has no fence in it. We put the fence there, and now we know it was always in the wrong place. JWST's discovery of the jumbios and the continuous mass function of planetary mass objects was not a single observation that can be treated as a footnote and set aside. It has fundamentally altered the telescope's science program for substellar objects, and it has triggered a cascade of follow-up investigations that are either already underway or already scheduled. Let me walk you through what is actually happening right now. Or as close to right now as a telescope in deep space 1.5 million kilometers from Earth allows. The first major follow-up program is the ongoing spectroscopic survey of JWST candidates in multiple star-forming regions beyond Orion. Corgrian and Pearson's original paper was based on imaging data. It identified objects by their appearance and their brightness. Imaging can tell you where objects are and roughly how massive they might be. Spectroscopy tells you what they're made of, and critically, how they formed. Webb's NIRSpec instrument is now taking detailed spectra of the most interesting JWST candidates, particularly the binary pairs, because binary systems carry information about formation processes that single objects don't. 2 objects orbiting each other must have formed close together, which places constraints on whether they could have been ejected from separate planetary systems. Preliminary spectroscopic results from the binary JWSTs discussed by the team at the European Astronomical Society meeting in mid-2024 suggest that the paired objects share very similar chemical compositions, consistent with having formed from the same parcel of gas rather than having been ejected separately and subsequently captured. This is evidence against the ejection model and for the in situ formation model. It is not conclusive. The sample is still small, but it tips the scales. The second major follow-up involves Rho Ophiuchi, another stellar nursery, this one only about 390 light-years from Earth, making it the closest star-forming region to our solar system. It's so close that Webb can resolve individual objects down to masses even below 1 Jupiter mass. Dr. Alicia Canteloube, a researcher at the Laboratoire d'Astrophysique de Marseille, who has been involved in JWST's follow-up imaging programs, is leading a survey of Rho Ophiuchi designed specifically to map the low-mass end of the object population, in a region where the sensitivity advantages of JWST are most extreme. The preliminary results from this survey, discussed at the 2025 American Astronomical Society meeting in January, show that the continuous distribution seen in Orion is reproduced in Rho Ophiuchi. It's not a quirk of one particular region, it appears to be a universal feature of star-forming environments. Everywhere JWST has looked at the low-mass end, the boundary smears. The third line of investigation is arguably the most ambitious, a dedicated program to find and characterize free-floating planetary mass objects, not in nursery clusters, but in the general field, the ordinary background of space between stellar nurseries. This matters because if these objects are abundant in star-forming regions, they should also be drifting through the broader galactic neighbourhood, detectable as cold, dim objects, with the chemical signatures that JWST's spectroscopy has now calibrated. The so-called JWST Moving Object Sensitive Survey, informally called MOSS by some team members, though it's not yet an official program name, is in the proposal and planning stages, seeking to use Webb's infrared sensitivity to detect and characterize isolated planetary mass objects within a few hundred light-years of the Sun. If successful, it would give us the first complete census of the nearest population of these objects, and potentially reveal whether they are common enough to constitute a significant fraction of the galaxy's overall mass budget. That last point, the mass budget question, is one that the cosmological community has been paying close attention to. Dark matter is the invisible material that makes up roughly 27% of the universe's total mass energy content. One of the early candidates for dark matter, now largely ruled out but occasionally resurrected, was a class of compact low-luminosity objects called MACOs, massive compact halo objects. The thinking was that the galactic halo, the extended spherical region surrounding the Milky Way's disk, might be full of dim, hard-to-detect objects like brown dwarfs and cold white dwarfs, collectively accounting for a significant fraction of the missing mass. MACO candidates were largely ruled out by gravitational microlensing surveys in the 1990s and 2000s, which showed that there aren't enough compact, massive objects in the halo to explain the observed dark matter. But those surveys had limited sensitivity to very low mass objects. Objects in the planetary mass range were essentially undetectable. JWST's new census of free-floating planetary mass objects is unlikely to restore MACOs as a major dark matter candidate, but it will refine our understanding of the total mass in low luminosity objects, which is a genuine gap in the accounting. Finally, there is a direct implication for the study of exoplanet atmospheres, which is, arguably, Webb's most publicly celebrated scientific contribution to date. When Webb takes a spectrum of an exoplanet atmosphere, it is comparing what it sees against models. Those models are built on our understanding of how temperature and chemistry interact in substellar atmospheres. The free-floating GWMBOs are, in a very real sense, giant planet atmospheres walking around without planets attached to them. They're uncontaminated by the light of a host star, which means Webb can study their atmospheric chemistry in isolation, without having to do the complex subtraction of stellar light that makes exoplanet atmosphere studies so technically demanding. Every spectrum Webb takes of a jumbo is, simultaneously, a direct observation of a cold giant planet atmosphere and a calibration point for the models used to interpret every other exoplanet spectrum. Dr. Artigau at Montreal has been explicit about this in multiple talks. The jumbos, he said at a conference in 2024, are the Rosetta Stones of giant planet atmospheres. We can stare at them as long as we want without worrying about the star. There's a fourth line of investigation that I've been wanting to bring in here because it connects the Jumbo story to something that will be a major driver of JWST's science program for the rest of this decade. And that is the question of directly imaged exoplanets. Most of the exoplanets we've discovered, the 5,000 and counting confirmed worlds in the exoplanet catalogue, were found by indirect methods. The transit method detects a tiny dimming of a star's light as a planet passes in front of it. The radial velocity method detects the tiny wobble a planet induces in its host star as they orbit their common centre of gravity. These methods are extraordinarily productive, but they tell you about the planet's size, mass, and orbital period. To characterize an atmosphere, to take a spectrum and find out what the planet is made of, you need to either observe the planet transiting its star, which only works for planets in close orbits around their stars, and which requires the star's light to contaminate everything you measure, or you need to directly image the planet, to actually resolve it as a separate point of light from its star. Direct imaging is hard. Stars are billions of times brighter than the planets orbiting them. Finding a planet in a direct image is like trying to spot a firefly hovering next to a searchlight at a distance of several kilometers. Before JWST, only a handful of exoplanets had been directly imaged, all of them young, hot, massive planets in wide orbits around their stars. the only category bright and far separated enough to be distinguishable from the stellar glare. Webb has been changing this. Its coronagraphic instruments, systems that physically block the light of a star to reveal faint objects nearby, have already produced new direct detections and unprecedented spectroscopic characterizations of known directly imaged planets, HR A799b, C, D and E, a system of 4 giant planets orbiting a star 130 light-years from Earth, were studied by Webb in 2023, yielding the most detailed spectra of young giant planet atmospheres ever obtained for any directly imaged system. But here's where the jumbos become crucial. The atmospheric models Webb uses to interpret the spectra of directly imaged exoplanets, like the HR 8799 system, are calibrated against brown dwarf spectra, because brown dwarfs are the best analogues for young giant planet atmospheres being roughly similar in temperature, gravity, and chemical composition. Before Webb, the brown dwarf calibration library was built from warm L and T dwarfs. Y dwarfs, the coldest brown dwarfs, whose temperatures overlap with those of mature Jupiter-like planets, were so poorly characterized that the models were essentially extrapolations in that temperature range. The jumbos and the cold free-floating objects Webb has now characterized in Orion, IC348, and Rho Ophiuchi have given atmospheric modelers a library of calibration objects in exactly the temperature range, 300 to 800 Kelvin, that corresponds to the atmospheres of the most interesting exoplanet targets, planets old enough to have cooled to these temperatures, planets that might, under some models, be in the range where atmospheric chemistry begins to look like it might support complex organic molecules. Dr. Brittany Miles at the University of California, Santa Cruz, who has been leading several of JWST's brown dwarf and directly imaged planet spectroscopy efforts, has described the cold free floaters as the missing rungs on the ladder. The ladder being the temperature sequence that connects the warmest, most well-characterized brown dwarfs to the coldest, most interesting exoplanet atmospheres. Before Webb, several rungs of that ladder were either missing or very poorly measured. After Webb's first 2 years of cold substellar spectroscopy, the ladder is nearly complete. This has an immediate practical consequence. When NASA's Nancy Grace Roman Space Telescope launches, currently planned for 2027, it will conduct a direct imaging survey of the galaxy, covering roughly 100 times the area of previous surveys. It will detect thousands of directly imaged planet candidates. Every one of those detections will need to be characterized spectroscopically. The models that will be used to interpret those spectra are being calibrated right now using jumbo and cold brown dwarf spectra from Webb. So the jumbos are not just interesting in their own right. They are, in a very practical sense, the training data for the next generation of exoplanet characterization. The objects that broke our classification system are now being used to build the tools with which we'll understand the next 10,000 worlds. There is something almost comic about that. The objects we couldn't name are now teaching us how to read the atmosphere of every planet we'll find in the next generation of surveys. Let me step back from the scientific detail for a moment and ask a bigger question. Why does it matter how we classify these objects? Why should anyone who isn't a professional astronomer care whether the line between planets and stars moves by a few Jupiter masses, or whether the categories get reorganized? The answer is not about taxonomy. The answer is about what these objects tell us about how the universe makes worlds. We live on one of those worlds, and for a very long time, most of human history, we had no idea how it got here. The idea that planets form in disks of material around young stars, that they coalesce from dust grains over millions of years, that Jupiter swept through the inner solar system early in its history, and shaped the distribution of material that eventually became the terrestrial planets, including Earth. All of this is knowledge acquired in living memory. The core accretion model that describes Jupiter's formation was formalized in the 1970s. The disk instability model was developed and debated throughout the 1980s and 1990s. The NICE model, the simulation of the early solar system's dynamical evolution, that predicted the late heavy bombardment was published in 2005. We are still, in geological terms, in the infancy of understanding how our own solar system came to be. The Jumbos complicate this story in a specific and important way. If objects of 1 to 5 Jupiter masses can form by direct collapse from nebular gas, without disks, without a parent star, without any of the scaffolding we associate with planetary formation, then the process of making giant planet-scale objects is far more common and far more diverse than we thought. This matters for the frequency of planetary systems like our own. It matters for the habitability of the universe. And it matters in a more philosophical sense. If the boundary between planets and stars is smeared, then the category of planet is not a sharp-edged container, but a fuzzy region in a continuous space of object types. That fuzziness has implications for the great question underlying most of JWST's science program. Are we alone? The search for life beyond Earth rests on identifying planets, specifically Earth-like planets in the habitable zones of Sun-like stars. The definition of what counts as a planet is not a bureaucratic formality. It shapes which objects get included in biosignature searches, which atmospheric spectra are interpreted through the lens of habitability, and which worlds are considered candidates for future missions. If the category is fuzzy at the high mass end, if there are planets that are too massive and too hot to be habitable, blending into brown dwarfs, and if the category is fuzzy at the free-floating end, if there are planets that orbit nothing and are warmed only by their internal heat, then the category-based approach to the search for life starts to show cracks. This is not a theoretical concern. Dr. Sarah Seeger at the Massachusetts Institute of Technology, who has spent her career developing the theoretical framework for detecting biosignatures in exoplanet atmospheres, has written about the need to think beyond Earth-like planets in the habitability conversation. Could a free-floating planetary mass object, warmed from the inside by residual heat from its formation, sustain liquid water in its subsurface? The answer, under some models, is yes, for the first billion years or so of the object's existence, before it cools below the threshold. These are not worlds we'd consider habitable in the traditional sense. But they're not entirely impossible either, and JWST has now confirmed that these objects exist in large numbers. Dr. Madhusudan's group at Cambridge has already begun modelling the atmospheric chemistry of the coldest known free-floating planetary mass objects, asking whether, under the temperatures and pressures measured by JWST spectrographs, there are windows of chemical complexity that might be relevant to prebiotic chemistry, the kind of chemistry that precedes life. It is very early days, the models are speculative, but the fact that this line of inquiry exists and that it's being pursued by serious scientists using real data reflects how deeply JWST has shifted what's considered an interesting question. There is a more personal dimension to this as well. Every culture in human history has had some version of the question, what are those lights in the sky? For most of that history, the lights in the sky were divided into two categories, the fixed stars and the wandering stars, the planets. Everything was either one or the other. The word planet comes from the Greek for wanderer. The ancients were not wrong to use a different word for objects that moved against the fixed background of the sky. Those objects were different in important ways, but the category was drawn around the observational behaviour of light, not around the physical nature of the objects themselves. Science has been revising and complicating those categories ever since. Uranus was discovered in 1781 and immediately created a controversy. It looked like a planet by the old definition but moved too slowly, had the wrong colour, the wrong apparent size. Neptune was predicted from the perturbations of Uranus's orbit before it was seen, which meant a category of object that influences observable objects existed before the object was found. Pluto was discovered in 1930 and classified as a planet, only to be stripped of that designation in 2006 when the IAU formally defined what a planet is for the first time, and Pluto, sharing its orbital neighbourhood with hundreds of Kuiper Belt objects of comparable size, didn't make the cut. Every revision of the category planet has been accompanied by controversy, discomfort, and eventually acceptance. The acceptance comes because the revision always illuminates something. It always reveals that reality is more complicated and more interesting than the category it was replacing. Pluto's reclassification taught us about the Kuiper Belt and the structure of the outer solar system. The broadening of planet to include hot Jupiters taught us about planetary migration and the chaotic early lives of planetary systems. And now, JWST's revelation that the boundary between planets and stars is smeared across a continuous range of masses teaches us about the full diversity of ways the universe can build an object. From the largest stellar furnaces down to the smallest free-floating orbs of methane-clouded gas drifting alone in the dark between the stars, the boundary was never clean. We just couldn't see clearly enough to know that. I want to push on the habitability question a little further here because I think it's under-discussed and because JWST's findings give it a new texture, the conventional framework for thinking about habitability, the one that drives the target selection for missions like the Habitable Worlds Observatory, the concept mission currently in the early planning stages at NASA, as a potential successor to Webb, centres on what's called the classical habitable zone. Think of it like the band of temperature around a campfire, where you can sit comfortably without freezing or burning. Too close to the fire and you're too hot for liquid water to exist on a planet's surface. Too far and the water freezes. In between, roughly where Earth sits relative to the Sun, liquid water is possible. The habitable zone is defined as the range of orbital distances where a planet with Earth-like composition could maintain liquid water on its surface. This is a reasonable starting point, but it's a starting point built around two specific assumptions: that the planet is in orbit around a star, and that the energy source for warming the planet is stellar radiation. Take away either of those assumptions and the habitable zone concept doesn't directly apply. Free-floating planetary mass objects have no star. They receive essentially zero stellar radiation, but they are not cold from the moment of formation. An object of 5 Jupiter masses, freshly formed by cloud collapse in a stellar nursery, begins its life at temperatures of thousands of Kelvin. It is hot. Internally hot, warmed by the energy of its own gravitational contraction, and by the residual heat of formation. It cools over time, slowly at first, then faster, eventually reaching the white dwarf temperature range and continuing downward over billions of years until it becomes, for all practical purposes, an invisible cold sphere of hydrogen and helium and trace compounds floating in the dark. But in the first few 100 million years of its existence, a free-floating planetary mass object is warm enough to potentially maintain liquid water. Not on a surface. These objects don't have surfaces in the way that rocky planets do. They're gas objects through and through, but in their atmospheres. At the right pressure level in the atmosphere of a young, warm, free-floating object, temperatures and pressures might sit within the range where liquid water droplets form, where water chemistry happens, where the building blocks of more complex molecules are stable. Dr. Sarah Seeger at MIT, whose work on biosignatures and atmospheric characterization has shaped the entire field of exoplanet science, has written about this possibility in a speculative but scientifically serious paper co-authored with Dr. William Baines in 2022. The paper asks, under what conditions might life arise in the atmosphere of a gas world, not on the atmosphere? The scenario is not as wild as it sounds. On Earth, we know that bacteria and other microbial life exist in the upper troposphere, suspended in cloud droplets, taking up nutrients, reproducing, dying, cycling. The conditions in a young, free-floating planetary mass object's atmosphere are not Earth-like. But the question of whether some form of chemistry complex enough to be called prebiotic might occur there is not obviously ruled out. Seeger is careful to note that this is highly speculative. The paper doesn't claim that life exists in the atmosphere of young, free-floating objects. It asks whether the conditions for chemistry of sufficient complexity are met. The answer in the paper's assessment is possibly. In some atmospheric pressure and temperature windows, for some fraction of the object's early lifetime. Possibly. JWST has now confirmed that young free-floating planetary mass objects exist in large numbers in stellar nurseries throughout the galaxy. Their atmospheric conditions, temperatures, pressures, chemical compositions are now being directly measured for the first time. The spectra Webb is taking of these objects are the first empirical data that can be used to test whether the atmospheric windows Seeger identified are actually present in real objects, not just in models. The data is very early. The analysis is in its infancy. No claim of prebiotic chemistry in a jumbo atmosphere has been made, and I want to be absolutely clear about that. What has been made is a set of detailed spectroscopic measurements that are now allowing researchers to ask the question seriously, with real data, for the first time. That is a different scientific moment from the one before Webb existed. Before Webb, the question was theoretical. After Webb, it is empirical. The objects exist. The spectra exist. The chemistry can be studied. Whether the answer turns out to be no, these are boring cold gas balls with no interesting chemistry, or something more surprising, we don't know yet. But the question is now in the domain of science rather than speculation, and that transition from untestable speculation to testable hypothesis is precisely what major observatories are built to make possible. There is one more implication I want to cover before the closing reflection, and it's the one that I find personally the most arresting. It concerns not the objects themselves, but the number of them, and what that number implies about the odds. The Drake equation, the famous formula proposed by radio astronomer Frank Drake in 1961 to estimate the number of communicating civilizations in the galaxy, contains a term called FP, the fraction of stars with planetary systems. When Drake first proposed the equation, this fraction was completely unknown. We had exactly one example of a planetary system, our own solar system. Whether any other star had planets was an open question. By the mid-1990s, when the first exoplanets were confirmed, the answer began to emerge. By the time the Kepler Space Telescope finished its survey in 2018, we had enough data to estimate that essentially every star in the galaxy, almost all of them, has at least one planet. FP is close to 1. JWST's discovery that free-floating planetary mass objects are enormously abundant, possibly more numerous than stars themselves in some star-forming regions, adds an entirely new dimension to this accounting. The Drake equation doesn't have a term for free-floating objects. It assumes all planets orbit stars, but if there are 10 or 20 or 50 free-floating planetary mass objects for every star in the galaxy, and some estimates of the Jumbo population suggest numbers in this range, though the uncertainties are still very large, then the sheer number of worlds in the universe is larger than any pre-JWST estimate suggested. Most of those worlds will be cold, dark, and inhospitable. Most will be gas objects with no surface, no stellar warmth, no obvious energy source to drive the chemistry of life. But the number is so large that even an astronomically small probability of interesting chemistry becomes meaningful. This is the arithmetic of wonder. When the denominator is unimaginably large, even a tiny probability in the numerator produces a real number, not a certainty, not an expectation, but a real non-zero number of possibilities drifting silently through the interstellar medium, uncatalogued, unnamed, orbiting nothing, warmed by nothing, except the slow leak of their own formation energy into the cold between the stars. We don't know if any of them are doing anything interesting. We may never know, for most of them, whether they even have atmospheres worth studying. But we know they exist. Webb told us so. And knowing they exist is the first step, and the only step, that has ever preceded every discovery science has ever made. There's a question I've been sitting with since I first read McCaw-Green and Pearson's paper, and I haven't found a satisfying answer to it. I'm not sure one exists yet. The question is this: what does it mean to be a planet? I don't mean in the bureaucratic sense, the IAU's formal criteria, the clearing the orbital neighbourhood language that everyone argued about when Pluto was demoted. I mean it in the deeper sense. What is the thing that we call a planet, at the level of physics and chemistry and formation history? such that it is meaningfully different from the things we call stars and the things we call something else. For most of my life, for most of anyone's life who has been watching science develop, the answer seemed clear. A planet orbits a star. It's too small to fuse hydrogen. It formed in a disk. It might have an atmosphere. It might have a surface. It might, under the right circumstances, have liquid water. It might have life. The category planet was not just a classification. It was a container for the most interesting question in science. Are we alone? JWST has not broken that question, but it has shown us that the container is porous, that objects of planetary mass drift free of any star, warmed only from within, that the chemical signatures we use to identify planetary atmospheres appear continuously across a range of masses that blends into what we use to call the bottom of the stellar sequence, that the universe makes Jupiter-scale objects in ways that we didn't model and didn't predict, and that those objects outnumber, in some star-forming regions, what our models would suggest. This does not make the universe less hospitable. It doesn't make the search for life less meaningful. It doesn't even necessarily make any individual planet less special. But it does mean that we're doing what science has always done when it's working at its best. We're replacing a clean map with a true one. The clean map was reassuring. The true map is stranger. The true map has objects in it that sit at the edge of every category we have. Too big for the smallest planets, too small for the dimmest stars, too cold for the youngest brown dwarfs, too isolated for anything formed in a disk. Objects that orbit each other through the dark between stars, carrying no name that fits them well, following no star's light, warming no moon's ocean. Just mass and gravity and the slow chemistry of cold hydrogen pressing against the edge of what is possible. Webb can see them now. That's the thing. For billions of years they were out there, and we looked past them because they were too dim and too cold and too far. We built our classification systems in their absence. We drew our lines and wrote them in textbooks and sent students home thinking the map was complete. It was never complete. The boundary was never where we said it was, and now we know that. And knowing it is better, stranger, more disorienting, more wonderful than not knowing. The universe hides things in its dimmest corners, not out of malice but out of simple physics. Light falls off as the square of distance. Cold objects barely glow, dust scatters and absorbs. For most of human history, the things we couldn't see didn't exist in our models. And then we built an instrument sensitive enough, cold enough, precise enough to look into those corners, and we found that the corners were full of things that don't fit our words, full of worlds that orbit nothing, full of objects that sit at the edge between what burns and what merely glows, between what formed in fire and what condensed in cold, between the last star and the first planet, blurring the line that we never had the right to draw so sharply in the first place. We don't have a final answer. We may not for years. The classification debate will continue. New surveys will be designed. More spectra will be taken. The IAU will eventually convene a working group and produce a revised definition, and someone will inevitably object to it. That is how science works. It is unglamorous and iterative and often inconclusive at any given moment, but what JWST has given us, what those 540 rogue objects in Orion, those 42 binary pairs, those continuous mass functions from 1 Jupiter mass to 80, those methane signatures showing up in objects we use to call brown dwarfs, what all of that has given us is clarity of a different kind, not the clarity of a resolved question. The clarity of a better question, and better questions are the only kind that lead somewhere real.